Welcome to section 11.2. So in this section, what we're going to do, which is really cool, is to move on from 2 dimensions and see how the concepts we've talked about either in the previous section or in previous classes expand to 3 dimensions. The precise objectives are to understand the 3-dimensional rectangular coordinate system, to calculate and analyze characteristics of 3-dimensional vectors, and to use 3-dimensional vectors to solve real-life problems. We'll see that it grows quite smoothly from 2 dimensions to 3 dimensions. One thing in math, when you want to find a more general rule, or when you want to go from 2 dimensions to 3 dimensions, is you always need to include the previous case, the smaller case. You want your generalization, your greater idea to include the specifics of the smaller situation you had before. Because 2 dimensions is part of 3 dimensions, so everything we did in 2 dimensions still needs to hold when we expand it to a 3rd dimension, and so on to 4, 5, 6 dimensions. Firstly, we will see that the one way we sketch the axis, or we define which one is the x, y, and z axis when we have the sketch of 3D, is the last one here. This might surprise us. We may have thought it was x and y because that's what we've always seen in 2D, and then we add z here. However, it does make sense to pick the 3rd one because when we have functions in 3 dimensions, it's going to be f of x and y, so we want it to be z equals f of x and y, and therefore we want the height to be the output. That's the way that it makes most sense. This is why it's similar to 2 dimensions. The output is how high the function is. So this and neither of those, and you need to always choose the x-axis to be this one and the y-axis to be that one, and then the z-axis to go up. Notice that x and y, you may wonder why it's x and y and not y and x. Well, because you want from x to y, you always want it to go in this direction. Orientation is important in math and physics, so this x to y, 90 degrees counterclockwise, is the same that we have in 2D. So how do we sketch points in 3D? It's very awkward. It's hard to visualize, but you just count the numbers on the x-axis and then on the y-axis, and then parallel to the z-axis. So here the point 1, 2, 4 is 1, 1, 2, 1, 2, 3, 4. Okay, so there's our point P. I'm using Nick O's great notes again. Thank you so much. You would not in general want to put these dashes, but we do it in this section 11.2 just to help us see kind of a 3D box where P is, because if we don't put dotted lines, then P could be in infinitely many positions, right? We don't know how deep it is. Something that's important is that when you go 1 in the x direction and then 1, 2 in the y direction, you want to make sure that you're not aligned with the 2 here, right? Because of the angle, because of the perspective, you are before 2. And likewise, when you go up 4 steps, you are not reaching the height of the tick here at 4. You are slightly lower, if I may say. Same with point Q, so we go 3, -1, 2. Almost always, when we draw in 3D, it's kind of difficult to see what's going on behind, so we will focus on the first octant, just like 2D has 4 quadrants, 1, 2, 3, 4. 3D has 8 octants, so we will focus on the first octant, and rarely will we draw what's behind the first octant. So the first octant is the one where x, y, and z are all positive. So this table here shows us how there are many formulas of 2D that naturally extend to 3D. This is quite a satisfying thing to realize, that really when you know stuff in 2D, you can just naturally logically expand it to 3D and it will still make sense. We had vectors v1, v2. Now we will see here vectors are just v1, v2, v3. There's just a new component. Distance formula. So what's the distance between 2 points in 2D? We use the Pythagorean theorem. It expands nicely in 3D. This is y actually. Let me just draw this in. If we are looking for the distance between this point and that point on the other side of the parallelepiped rectangle, you can do it in 2 steps. First, find the diagonal, which is Pythagoras in 2D, x squared plus y squared equals c squared, and then you have a brand new right triangle, which is a right angle here. I can't show it, but you can now do c squared plus z squared equals s squared. And what is c squared? It was found earlier, so therefore s squared is x squared plus y squared plus z squared. It's nice how Pythagoras can be expanded, and then if there was an extra dimension, let's say w, then we would do plus w2 minus w1 squared. What about the midpoint? If we have 2 points in 2D, this is the formula that you all remember. In 3D, it's just like that. And in 1D, it's just x1 plus x2 over 2. Equation of a circle, equation of a sphere. Again, very natural way of expanding something we know. Vectors we mentioned, magnitude of a vector. This is very strongly related to the distance formula because the magnitude of a vector is the distance between the tail and the head, the initial point and the end point. Finally, one formula that doesn't even change is how to find a unit vector. In 2D, you take the vectors component and you divide each one of them by the magnitude. Same with 3D. Of course, there's 3 components now, and to find the magnitude, it's a little bit different, but the general formula is just the same. So we can practice these things with an exercise that has several of these concepts. The distance between these 2 points, we will use the distance formula right there. To find the midpoint, we just use x1 plus y1 over 2, x2 plus y2 over 2. Sorry, x1 plus x2 over 2, y1 plus y2 over 2, z1 plus z2 over 2. You don't even need to write that. You may just be able to look at the points and see what the midpoint coordinates are. In order to find a unit vector, we'll just write what the vector is, and then we divide by its magnitude. Here's the answer. And finally, if we want to write the vector in standard unit vector notation, or using this is just the way we would prefer to write vectors, but using the standard unit vectors, this is what it looks like. So the new standard unit vector is written k, or if we had e1, e2, then it would be e3. Which is what we will do more often when we work with linear algebra in semester 2, because in linear algebra, the number of dimensions is often undefined. It's typically n. So a little exercise puzzle here. How would you find a vector that has magnitude 4 and is parallel to -2, -4, 5? The way to do that is to make an intermediate step where you find a unit vector parallel to v. So we look for the magnitude of v, we do v over magnitude of v, and now that we have a unit vector that has a magnitude of 1, we can multiply it by 4, and it'll give us what we were looking for. So if we call this magnitude 4 vector w, then w is -8, -16, 20, all over root 45. If you have 3 points in space and you wonder if they are on the same line, we call this collinear. You have a lot of options, but one of them is just to pick 2 vectors. You can You can take PQ and PR, you can take RP and PQ, you can take QP and QR, and just check if they are parallel, so if the vectors are proportional to each other. Here, we chose PQ and RP, so PQ and then RP goes from here to there, and the result was 2, 10, 2, as well as 4, 24. So flipping RP to give us PR, remember that if we have RP, then PR would just be -4, -20, -4. We find that PR is -2 times PQ, and therefore the 3 points are collinear. A little question here that is more easier than it looks. Is the point -7, 0, 3 inside, outside, or on the sphere, which is centered at 2, 5, -4 with radius 3? We don't even need to worry about the sphere itself. All we're going to do is to check for the distance between P and the center, and that'll give us the answer. If that distance is less than 3, we are inside. If it's exactly 3, we are on the sphere. And then if we get a distance that's more than 3, that means P is outside. Be aware that the sphere is a 2-dimensional surface in 3 dimensions. It's a very thin layer. If you are inside the sphere, that is not on the sphere. If the inside is included, then we would call this a ball. So a sphere is like just the peel of the orange, infinitely thin. So knowing that, let's calculate the distance between P and the center, and we get root 55 or root 155, which is more than 3, so P is outside the sphere. Finally, one last exercise, and for this exercise I will actually work through it because it's a little bit more complex, and then we'll come back here. Alright, let's see this exercise together. A television camera weighing 120 pounds is supported by a tripod, as shown in the figure. Represent the force exerted on each leg of the tripod as a vector and the magnitude of the forces. So we have a camera here, and its weight can be represented by a force that I'll call F, and clearly it's vertical, so the X and Y components are 0, and then since it goes down, it's -120. Now, these 3 legs of the tripod are supporting this weight. So basically, we could think about forces that go up like this, and together they should combine to cancel out the force F. We are not going to think about these that way. We are just going to think of the opposite forces F1, F2, and F3, F1, F3, and F2, that when added together equal F. So what we notice is that these 3 forces are each along the legs, so they are going to be a certain factor of the vector from P to Q1, from P to Q2, and from P to Q3. So firstly, let's write what PQ1 is. So it's OQ1 minus OP, which is 0, -1, and -4. What is PQ2? It's OQ2 minus OP, so it's √3/2, 1/2, and -4. And finally, PQ3 is -√3/2, 1/2, and -4. So in the example here, I've shown the vectors f1 to be a certain length, ending here. I don't know if it's longer or shorter, it doesn't matter. F is certainly a lot longer, but actually I know full well that PQ1 goes from P to Q1, but what is F1, F2, F3? It's actually a lot longer than PQ1, right? Because we are supposed to reach vector F, which goes down to negative 120. So the third component is negative 120, meaning that each of F1, F2, F3 is a lot longer than PQ1, but that doesn't matter. What we know is that force 1 is going to be a factor of PQ1. Force 2 is a factor of PQ2. And force 3 is a factor of PQ3. Now you may say, wait a minute, why are these the same factor? They might not be, and you're absolutely correct. They could not be the same factor, but in this particular case, however, the factor is going to be the same for each force, and the reason is that the points on the floor are on a circle, and the camera itself is exactly above the center. Moreover, the legs have the same length, so all of these things together tell us that the force is going to be spread evenly among these legs. So the points are on a circle with the camera exactly over its center, which we can also say the legs have the same length. So the force is spread. So the force is spread evenly along each leg. So that's why we can use the same factor K. So F1 plus F2 plus F3 is going to be equal to F. To see better what's happening, I'm going to write F1, F2, F3 in a column. So K times F1 is K times 0, negative 1, negative 4. F2 is K times root 3 over 2, 1/2, negative 4. And F3 is negative root 3 over 2, 1/2, negative 4. So if we add all of these up, we want to get F, which, as we know, is 0, 0, negative 120. So by observing the last column is the easiest one to figure out, we can clearly see that K is going to have to be equal to 10. Okay, so that allows us to now finish the exercise and write what F1, let me just go back to purple, F1 is equal to 0, negative 10, negative 40. F2 is equal to 5 root 3, 5, negative 40. And F3 is equal to negative 5 root 3, 5, negative 40. And just because we are asked also what is the magnitude of these forces, let's just write what the magnitude of F1 is, or let's put 1, 2, 3, because they're all the same. If you calculate that, it's 41.23. So the force is given in pounds in this exercise. So that's it. Okay, so you can either copy the what I wrote, or, which I find kind of neater, what Nick wrote here. The content is the same, and that wraps it for us for the notes form 11.2. Thank you for listening.